Thank you for joining today's presentation on the intersection of military applications and advanced learning technologies. My name is Dr. Nathan Gaw from the Department of Operational Sciences at the Air Force Institute of Technology. This is one of the two graduate military institutions in the United States. And today I will be presenting how federated learning is paving the way for innovative solutions in military strategy, cybersecurity, and medical applications within the military as well. So in today's presentation, I'll start by discussing the background and motivation behind our research. We'll explore case studies in military applications, including network intrusion detection and Parkinson's disease prediction. And our goal is to highlight the significance of federated learning in addressing these critical areas. So the modern military landscape is increasingly complex, requiring novel solutions that respect security and policy constraints. Federated learning offers a promising avenue, enabling collaborative machine learning without direct data sharing, and thus overcomes traditional barriers to data utilization and in sensitive environments. So here are a few examples where federated learning can be applicable in the military domain, and so I'll highlight a few of these. First is in cybersecurity. So within cybersecurity, federated learning can enhance these efforts by enabling collective learning of attack patterns and vulnerabilities across military networks and systems. My lab is currently doing collaboration with the Army Cyber Institute at West Point, and we've actually come up with a few interesting results, especially in the active learning and semi-supervised learning domains. Additionally, within the area of predictive maintenance for equipment, military equipment, including vehicles, aircraft, and weaponry, requires regular maintenance to ensure operational readiness. Federated learning can be used to develop predictive maintenance models by analyzing sensor data from equipment deployed in different locations. These models can predict failures or maintenance needs, optimizing maintenance schedules and reducing downtimes. And finally, maybe a little bit less expected for discussing within the military application, but health monitoring for personnel is also incredibly important. This is something that I personally have a background in for about 7 years, and so bringing this into the military context is still very important for me. And so within federated learning, this can be used to have individuals have wearable sensors or have some type of remote collecting devices such as smartphones to collect physiological data from military personnel in different locations. And by leveraging federated learning, healthcare providers can develop personalized health models while ensuring data privacy and security. So the first case study I present is on active federated learning for network intrusion detection. This research was conducted by one of my recently graduated master's students, First Lieutenant Matthew Sauer. He's currently stationed at Barksdale Air Force Base in Louisiana. So cybersecurity threats are growing increasingly complex, particularly for the U.S. military. Traditional detection methods are struggling to keep pace with the constantly evolving threats. The expanding Internet of Things landscape, comprising of billions of vulnerable devices, demands protective measures. Federated learning has demonstrated effectiveness in these IoT environments prone to cyber attacks. However, labeling all IoT data for model training is impractical due to its sheer volume. And so active learning emerges as a machine learning approach to address this challenge by reducing the need for extensive data labeling, and especially within the context of federated learning, and when it gets to such a large scale, this is incredibly important. In real case scenarios, we can't simply label all of the data. We have to come up with solutions to identify which parts of the labeled data are the most important. And so basic idea of active learning is it identifies which unlabeled instances within our data set are the most informative to label. So a model will predict on the unlabeled data set based on sampling strategy, and uncertain samples are labeled by a human / oracle. And so this figure below represents general idea behind active learning. So if we chose to just simply randomly label instances, we would get our middle figure here, which would maybe give us some useful advantage. But really what would give us the main advantage is what are the data instances right at that margin where we're the most uncertain about. And this is what will power our model to perform the most effectively. So our experimental setup includes a data set split among 4 different clients using federated average strategy, focusing on a binary classification task where we have a number of clients that have benign or malicious data packets coming into this cyber system, where we have a handful of different maligned data packages for each of these different clients, just to really show the ability of this framework to handle different instances. And so general strategies that we looked at for this is 1, no additional labels, only 1 attack and 1 benign label for the particular client. 2, randomly labeling samples, so just like that middle figure a couple slides ago. 3, querying the first 10 samples for which the model is uncertain. So we had a particular threshold that we used to identify uncertainty for labeling that particular sample. And then 4, querying the 10 most uncertain samples for that particular communication round. And so these 4 results indicate the performance of our model. And so as you could see, the one on the upper left-hand side just represents having 1 benign and 1 malicious sample and just letting the clients run. The second one is random query, and you could see there's quite a bit of variability and uncertainty in regards to that. The next one is labeling the first 10 uncertain samples as they come into the system. And then finally, we also have the 10 most uncertain samples, which produces, of a single communication round, which produces the most stable results. And so, as you can see, federated active learning has shown that it can achieve similar results with a lot less labeled data. Previous work used around 500,000 samples, while we labeled at most 2,000 samples to perform, which is only 0.4% of the data. And so this work shows the need to develop methods to overcome the large amounts of unlabeled data in the Internet of Battlefield Things. And these preliminary results are just one of the many things that we've been working on. But just something initial to show to you guys, showing the promising value of federated active learning. And so transitioning from cybersecurity, let's delve into medical applications of federated learning. The same principles that protect our networks can also safeguard our most precious asset, the health and well-being of our military personnel, which is something that I want to bring from my own background into the military context. And so we'll explore how federated learning is making strides in diagnosement and treatment of health conditions. I have done some work in post-traumatic headache, but we're going to do main focus into Parkinson's disease. Interestingly enough, there are a number of veterans that struggle with Parkinson's disease, actually higher than, it's shown that statistically higher amount of veterans deal with Parkinson's disease because during the Vietnam War, chemical agent, Agent Orange, was used against, and other herbicides was used against our military personnel, which has a much stronger chance of affecting somebody with Parkinson's disease. So traditional ML methods are unable to pull large amounts of data from health data due to privacy-preserving laws. So in the United States, that's HIPAA. However, with federated learning, that makes it possible for learning in a distributed fashion. So the next case study I will present is on adaptive client selection for Parkinson's disease prediction. The research was conducted by one of my PhD students, Jen Alsop, who is currently at Wright-Patterson Air Force Base. So Parkinson's disease is the fastest growing neurological disorder. Patients suffer from this disease and are highly heterogeneous in nature. So they can have problems with movement, tremors, voice impairment, memory issues, and effective treatment may slow down the progression. The typical measurement that's used to determine the severity of somebody's Parkinson's disease is the Movement Disorder Society Unified Parkinson's Disease Rating Scale, referred to as MDS-UPDRS. And one solution that we have been working on for the past few years is in the domain of telemonitoring, which is the use of electronic devices such as smartphones to remotely monitor patients. And so we will talk about a data set called the Empower data set a few slides from now, where we're able to collect different information about individuals with Parkinson's disease on a daily basis to quantify their disorder. So very typical in this application, So in the domain of Parkinson's disease, when somebody has Parkinson's disease, you don't know exactly what that means and what disease conditions they're experiencing. So everybody with Parkinson's disease has different expressions of that particular disease throughout that progression. And so knowing how to handle heterogeneous individuals or heterogeneous clients within a federated learning framework is very important. And so when clients are heterogeneous, the machine learning algorithm can experience significant problems during training, and non-independent and identically distributed data can lead to the global model not generalizing well and experiencing biases towards some of the clients, leading to slower convergence and suboptimal performance. So some ways to mitigate challenges from heterogeneous data is by performing client selection. Client selection algorithms estimate the value of federated learning clients and then adaptively sample valuable clients. There are many ways to determine clients' value, but the most common ways are to select clients that have the highest cumulative loss or high divergence from the global model, so we can improve general performance of the global model. And another method is to avoid noisy or malicious clients. And so there has to be a threshold to identify, at what point is somebody noisy client or malicious client, and we might not want to incorporate that client into our model training. And so there really is no one-size-fits-all solution, and it's typically very problem-dependent. And so, for this particular application, we really wanted to identify, what were those individuals that were, that present a good diversity of clients, but not too much. So we looked at 3 different adaptive client selection strategies. The first one was a greedy algorithm, looking at which clients in a particular round would improve the accuracy as much as possible. We also looked at another method called upper confidence bound, and this looks at a number of possible actions and distributions based on average past performance and number of times that action has been selected. We might not want to select the same client too many times in a particular communication round. And then also Thompson sampling, which is a Bayesian approach to selecting actions using beta distribution function for our prior and updating our beliefs after every communication round. So for our particular data set that we had 37 Parkinson's disease patients, for which we looked at those as our 37 different clients. We had the Empower smartphone app, which collected data daily from these Parkinson's disease individuals for a period of about 6 months. And there were 2 different features that were collected. One was voice features, and the second was tapping features. So as you can see, exercise was pretty simple for the voice features. It was asking the Parkinson's disease patient to say "ah" into the microphone for as long as they can. And through a variety of processing algorithms, we were able to obtain a handful of voice features. And then similarly with the tapping features, seeing how precise an individual's motor capabilities are. And users were instructed to tap between 2 dots as quickly as possible. And the main goal of this task is to predict the severity class with smartphone collected voice and tapping data. So here is a general setup for how we split up the clients. So to keep the model relatively fair, we did try to have a relative diversity of instances within initialization of the server, as well as a validation set and test set. And then the non-circled clients here are those individuals for which we will select during the model training process to try to perform as well as possible on that held out test set. And for our data pre-processing, we only consider the last entry of each day for the patients. So patients were instructed to collect data 3 times a day. We decided to do their last entry because it's probably the time where they're the most normalized. They've taken their meds and everything else. And we also standardized the features. Initialization, so we did 5 training rounds of initialization on those first 3 clients, and then we looked at these different client selection strategies. Here is the general outline of our test setup. So we had 5, 10, and 15 clients adaptively selected for each communication round. We wanted to see what number of clients do we have some benefit for adaptive client selection. We had 20 different communication rounds, and our model was a multi-layer perceptron, MLP, with 3 layers, with a ReLU activation function using an atom optimizer. And so for 5 clients, you can actually see that there really isn't any method that's significantly better than the federated average method here. And so we see that adaptively selecting 5 clients doesn't seem to be very beneficial. When you get to 10 clients, we actually see right here that UCB1 performs significantly better than all the other methods. And Thompson sampling performs pretty well as well. And we can also see at 15 clients relatively similar performance. So we can kind of see that our saturation is met around the 10 client round. And so in summary, the number of sample clients impacts statistical significance from baseline methods. When there are enough clients proposed, adaptive client selection methods performed significantly better than federated average. We found a UCB1 performed significantly better in most cases. There are a few cases where Thompson sampling performed better. And adaptive client selection methods can decrease training difficulties due to non-IID clients. And so, in conclusion, these 2 case studies demonstrate that federated learning can alleviate barriers to accessing the full potential of machine learning and AI to make strategic decisions and access real-time relevant data. Federated learning is especially desirable for military application, where the battlefield is dynamic, dispersed, and resource-constrained. And so with the expansion of IoT devices, researching and expanding the security and efficiency of federated learning from a military standpoint will become more prevalent. And so with that, I'd like to open up the floor for any questions that you might have for me.
Yeah. Thank you so much for the talk. It was very good. We've got a question already, and then Daniel. Okay, we'll take that one first.
Thank you for your presentation. So my question is related so are you planning to work also on decentralized fashion, maybe for the interested area that cannot reach internet, that cannot reach a central aggregator server?
Can you rephrase that question? I didn't quite hear what you...
So my question is, are you planning to work also on decentralized learning, maybe for interested area in which that cannot reach a central server, that cannot reach cloud, the internet, and so on?
Absolutely. And so, yeah, especially within the cybersecurity perspective, we're looking into applications too where, yeah, instead of focusing on the basic aspect of federated learning, updating a global model, there might be instances where it may make sense to have clients adaptively serve as the training in the global model in different perspectives. One particular aspect is in the context of space. So I'm actually working with some folks from University of Central Florida where we're looking at applications where, learning is very decentralized, and even the global model, it almost makes sense to trade spots with different clients just because of, the aspect of space. So there's, much less communication up there. And so, we're looking into some applications in regards to that.
Thank you very much.
Ruth, let's take the gentleman at the back.
Thanks very much for the interesting talk. So, can you elaborate on the role of privacy when you apply federated learning in cybersecurity context? If all the devices belong to one military base, why won't you just concatenate them, just run regular machine learning on the central?
Yeah, that's a good question, and I think it requires some thought for the particular cybersecurity network that you're looking at. And so, there might be some cases where that would make sense, within your particular IoT system to have things separated from each other, even within a single military base, because you would want to avoid leakage of malicious data packets from one area in an IoT system to another. And so keeping it private can be helpful.
Yes, but that is privacy. You need authenticity. But in order to authenticate data is different from to preserve the privacy of the data. By preserving the privacy, you won't solve the authenticity of the data, right?
Yeah, that's actually a really good point as well. And so, within a military base, if there is some method to authenticate the data packets, that might not necessarily be quite as important. And so, we look at this context with, even collaborating with a variety of other, allied countries. And so, sometimes, although we are friendly with, various other allied countries, it might still be good, in everybody's interest to keep our data private with each other and not share. And so, probably, you do make a good point about the authentication. If there's a way to authenticate the data, it might not be, necessarily as important. That data can be locked, within particular IoT systems. But, definitely, for collaborating with other military and allied military, it can privacy can still be of some importance. But you do make a great point in regards to the authentication.
We're going to take a question from online.
Well, a quick question about the Empower dataset, the Parkinson disease. Will this dataset publicly available? So if not, do you have a plan to make it public?
Yes, the Empower dataset is publicly available. You have to go through an approval process to get access to the data. For the person online who asks, you can contact me at nathan.gaw@affit.edu. I can tell you how to get access to that data. Again, you have to go through approval process, but it doesn't take too long to get access to the data.
Cool, thanks so much.
Let's thank Nathan for the great talk. Thank you so much.